first of weekly, or then we can cover up the later other topics. So I will start with the atomic spectra problem today. First problem. The problem reads: the allowed states for He helium-2p2 configuration are. So the question is from LS coupling or JJ coupling. So the allowed state for He2p2 configuration. Now the helium in the ground state is 1s2 2s2, 1s2 2s2. So when two of the electrons from 2s2 jump to 2p2 orbitals, we have to calculate the configuration or the spectroscopic terms which we get. So it is basically two electrons in the 2p orbital, one in the 1px and one in the 1py. Sorry, not 1py. The 2py and 2px orbital. So both are upspin. So the first electron spin S1 is equal to half. The second electron spin S2 is equal to half. And L1 and L2, the p orbit, L1 and L2 will be 1. Since both the electrons are there in the p orbit, we have got L1 and L2 equal to 1. So L1 equal to 1, L2 is equal to 1, S1 is equal to half. There is a mistake. S1 is equal to half, S2 is equal to half, both upspin. In the LS coupling, we have to couple first L1 and L2 to get L, couple S1 and S2 to get S, and then couple capital L and capital S to get capital J. So this is the LS coupling. I have written as LS coupling, L1 plus L2 equal to capital L, S1 plus S2 equal to capital S, and finally capital L plus capital S equal to capital J. So that is the thing of the LS coupling. Now L1 equal to 1, L2 is equal to 1. L values, different L values going from mod of L1 minus L2 to L1 plus L2. So L1 and L2 are 1 and 1. So L1 minus L2 to L1 plus L2, the different allowed values of capital L are 0, 1 and 2. L1 minus L2 mod to L1 plus L2 with a gap of 1. So allowed values of L is 0, 1 and 2. Allowed values of S are S1 equal to half and S2 is equal to half. So mod of S1 minus S2 to S1 plus S2. So the allowed values of S are 0 and 1. The allowed values of S, capital S, are 0 and 1. So we take the permutations and combinations of all S and all L and all S values and arrive at the term value. So we take the combinations of all L and all S values. So I have tabulated it. Different values of L values are 0, and along with that S value is 0, and L value 0, S value 1, and L value 1, S value 0, S value 1, L value 2, S value 0, and S value 1. 2 S values are there and 3 L values are there. So we will have the different J values. So J values will get from L minus S, capital L minus S to capital L plus S. So I will take one example. L value is 0 and S value is 0. J value can be only 1, that is 0. And the spectral term it gives rise to is 2S plus 0, 2S plus 1 LJ, 2S plus 1 LJ. Okay, 2S plus 1 LJ. You have to prepare the spectral term. S is first tabular value column. S is equal to 0. You will get 2S plus 1 is equal to 1, and then you will get L value is for this particular first column, first row is L value is 0. So S will write the symbol S, and then the J value is 0. Next one is I will take L is equal to 1 and S is equal to 1. L is equal to 1 and S is equal to 1. different j values are 0, 1 and 2, L minus S to L plus S, 0, 1 and 2, and we'll write 2s plus 1 value for that, that is 3. 2s plus 1 value with L is equal to 1, L is equal to, with S is equal to 1 is 3, and L is 1, so 3p, and different j values are 0, 1 and 2. So 3p0, 3p1 and 3p2. These are the three terms. Likewise, I have written for all the spectral terms. We have to do capital L minus S to capital L plus S, and that particular L value we have to write either S, P or D, and then we have to go ahead with the writing the J values at the bottom. So this is the LS coupling problem. So I move to the next problem. That is the if an atom is in the 3D state.
Bhushan sir, just a thing that can you use your mouse pointer hovering over the slide so that people can see where you are in the slide? Because of buffering, some people miss out.
Can you see the mouse pointer now?
Yes, sir. Yeah, please go ahead.
Fine. So if an atom, okay, fine. In the table where I will indicate. Okay, if an atom is in the 3D3 state, the angle between its orbital and spin angular momentum vector, capital L and capital S is that is the cos inverse. Different values are there. So the 3D3 state, we can see that you compare with the 2s plus 1 Lj, and you will get S is equal to 1, L is equal to, for d orbit, L d orbit L is equal to 2, and my J value here is 3. My J value is 3. So S is equal to 1, L is equal to 2 for the d orbit, and J is equal to 3. Now I'm just calculating LL plus 1, SS plus 1, and JJ plus 1 value. Sorry, the LL plus SS plus 1 value is 2, and JJ plus 1 value is 12. Okay. So what we do is, according to quantum mechanics, L square eigenvalues are LL plus 1 across square, and I have written one. I have written one of them. I have not written LL plus 1, and that equality is also not there. So LL plus 1, when it acts on the wave function, the angular part of the wave function, it will give LL plus 1 x cross square y lm of theta phi. So the eigenvalues of these angular momentum, when it acts, it will give LL plus 1 and SS plus 1 and JJ plus 1. So we are using these values, LL plus 1, SS plus 1 and JJ plus 1. So according to vector algebra, J square is equal to L square plus S square plus 2L dot S. This is the triangle law of vector addition. So when it goes with quantum mechanics with the wave function, it will lead to JJ plus 1, LL plus 1, SS plus 1, and the 2L mod of L and mod of S and cos theta. That is where we get the angle between the L and the S vectors. Okay, so L and S vectors coupled to give the J, and the angle between L and S is decided by this cos theta. So in terms of quantum mechanics, cos theta is equal to J plus 1. You can move this LL plus 1 and J plus 1 onto the left hand side to get the value of cos to the left hand side to get the value of cos theta. We will get cos theta equal to JJ plus 1 minus LL plus 1 minus SS plus 1 divided by 2 root of the modulus of L and modulus of S here, because here square root of LL plus 1 and square root SS plus 1 coupled to give square root JJ plus 1 actually. So cos theta, if you substitute all the values, L is equal to 2, J is equal to 3 you use, and S is equal to 1, all those values if you substitute, you will get cos theta JJ plus 12 minus 6 minus 2 divided by 2 into square root of 6 into square root of 2. So cos theta is 1 over root 3. In my slides, I have marked the correct answer by the bold. And here the correct answer is A. So I have marked that in a bold letter option, bold option. Okay. So the angle between the L and S for the 3D3 state is for the 3D3 state is cos inverse of 1 by root 3. So that is the inference from our this thing. Okay, the coupling of LS coupling. Okay, now one of the important problems here in spectroscopy is the ground state. When different term values are given, spectral terms are given, what is the ground state? I have not taken any problem here in this seminar, but I have put those problems in the quiz. So different term values are there. You want to find the which is the lowest or the ground state term value. So the rules for that I have mentioned here. So the state will with highest multiplicity will have state with highest multiplicity will have lowest energy. So if you see these term values, which are there here 1s03, p03, p1, 3p2. Out of that, the state with the highest multiplicity 3p0, 3p1, 3p2 will have the lowest energies. Then if the states have the same multiplicity like 3p0, 3p1 and 3p0, 3p2, 3p0, 3p1 and 3p2, then the state with the lowest with the highest L value will have the lowest lowest energy. So there are different states 3p, 3p, 3d, like that. Then the state with the lowest highest L will have the lowest energy. So that is the one rule. And with the if the states have the same multiplicity and the same L value like 3p0, 3p1 and 3p2, if the states have the same multiplicity and the same L value, then the lowest J will have the lowest energy. Lowest J, that is 3p0, will have the lowest energy provided the cell is less than half filled. Provided the cell is less than half filled. Otherwise, it will be the opposite of it, I suppose. So when 3p half, when 2p half and 2p 3 half, two states are there. 2p half and 2p 3 half states are there in the sodium atom. It is less than half filled, so p half will be lower in energy. If the case is for chlorine 17, where the shell is more than half filled, then it will be 2p3 half will be lower in energy. So the same S values, state with lower J will be lower in energy when it is less than half filled. When it is more than half filled, when it is more than half filled, then it will be the opposite. The state with a higher J will be lower in energy. So I'll go to the next slide. That is regarding the Zeeman effect. The slide is regarding the Zeeman effect. So I'm putting the atomic spectra, LS coupling, JJ coupling, the Zeeman effect, and the molecular spectra. So the question is the D1 and D2 lines of sodium. The D1 we get from 2p half to 2s half transition, and the D2 line 2p3 half to 2s half will split on the application of magnetic field into how many lines? That is the first line 2p half into 2p half to 2s half, how many lines it will split, and the second how many it will split. So while drawing the spectrum, you have to draw like this. So due to the spin orbit coupling, my this 2p or 2p will split into 2p half and 2p3 half. 2p half will be lower in energy. So this 2p3 half, as I am mentioning here, will split into 4 levels, 2j plus 1. 2p half will split into 4 levels. This 2p half will split into two levels, 2j plus 1. So this will split into 4 levels, this into 2 levels, this into 2 levels. Now, according to the selection rules of the Zeeman effect, that is delta mj equal to 0, this gives rise to pi components, and delta mj equal to plus or minus 1 gives rise to sigma component. According to these selection rules, the lines will split. You can see here that this set of levels is half to minus half, minus half to minus half, half to half, and minus half to half. These are levels for this 2p half to 2s half transition, which is the D1 line. So it will split into four transitions we'll get for these with different energies. So this D1 line is into this D1 line is splitting into 4 transitions, and similarly this is half to minus half is delta mj is equal to minus 1, half to half is 0, minus half to half is some plus or minus 1. So we get the D1 and D2 lines of the sodium, and you can see as from the figure 4 lines for the splitting for 2 p half to 2s half, and 4 p half to 4s half, and then the 6 lines for the 2p3 half to 2s half. So like this, there are the transitions for the D1 and D2 lines of the sodium. Okay, so D1 and D2 lines of sodium split into 4 and 6 lines respectively. So this is regarding the simple selection rules of the Zeeman effect. Simple selection rules of the Zeeman effect. Now I go to a little complicated problem from the Zeeman effect, that is from the next examination, that is an atomic transition. Suppose say your sodium line is there, your that Zeeman effect, without the Zeeman effect, it will have D1 and D2 lines due to transitions from 2p half to 2s half, and 2p half to 2p3 half to 2s half. So 2 lines will be there, D1 and D2. When the application of the magnetic field is there, these 2 lines, D1 and D2, split due to the Zeeman effect. So what is the change in the wavelength? So the D1 and D2 lines, wavelength is 5890 angstrom and 5896 angstrom. Still it will split, slight splitting of the order of very small order compared to that 5890, 1 to the power 10, 1 by 10 raised to 4 or 10 raised to 6. We'll see what it is splitting into. So it is splitting into 0.01 nanometers. That slight split is 0.01 nanometers. The answer is that. So we'll go to that problem. So so we have taken the singlet line. So there is a 1p to 1s transition. Suppose say 1p to 1s transition. Originally there is no D1 and D2 lines, only one transition is there, and when that one transition is there, it will split into 1p state. Due to after the application of magnetic field, it will split into 3 lines, and this will give rise to normal Zeeman triplet or normal Zeeman effect we will get. I was discussing the anomalous Zeeman effect in sodium. Now when the one singlet line splits, it will give rise to normal Zeeman effect. Okay, the normal Zeeman effect we will observe. So let us see what is happening. So the 1p orbit, the 1p line splits into 3 with mj equal to 0 and plus or minus 1. So plus 1 is above, 0 is at its original place, and minus 1 is below that. So it splits into that the delta E, the spacing between 0 and plus 1 or minus 1 line is delta E, that is given by G mu B, the G factor mu B, Bohr magneton, and applied magnetic field, and delta mj value. Here the delta mj is just 1, so delta mj value, so it will give G mu B B, G mu B B. So the question is approximate the splitting of the separation in the Zeeman spectral line is approximately. So approximately I'll neglect a G factor over here, and you will get G mu B B. So G is neglected, approximately equal to mu B B, because mj is 1, delta mj equal to 1. So mu B B is the uh, energy level, splitting in the energy level delta E. So delta nu is mu BB by H. So mu BB by H. So I have derived it over here. E is equal to H nu, Hc by lambda. So delta E is H delta nu. And if I differentiate this one, Hc by lambda, E delta E is equal to H delta nu, and Hc by lambda, if I differentiate to get C by lambda square delta nu. This is the most crucial step over here. Okay, so Hc by lambda square, like error formula or just differentiation, to do that Hc by lambda square into delta lambda. So from that you get delta lambda expression, and now I put the values of lambda is equal to 215 to 10 raised to minus 9 meters. Mu b is equal to 9.7 in SI units Euclid, and the Planck's constant and the velocity of light. You will get delta nu, the splitting in terms of wavelength of the Zeeman spectral line is 0.01 nanometers. 0.01 nanometers, which is option A. Okay, option A. So we are completed with the Zeeman effect, and in the quiz we will have problems from the Zeeman effect, also similar problems. Now I go to the rotational spectra. The basics of the rotational spectra first I will explain, and then I'll go to the problems of the rotational spectra. So which molecules will show me the rotational spectra? The rotational spectra is shown by the molecules with the permanent electric dipole moment. HCl is having permanent electric dipole moment. So HCl is more electronegative than H. So the electron is shifted towards the in the ionic bond between H and Cl. The electron is more displaced towards the Cl molecule, Cl atom, and the Cl is having a partial negative charge, and H is partial positive charge. So it is having a permanent electric dipole moment, and these molecules will show rotational spectra. H2O2 and N2, when there is no displacement of the electron towards a single atom, so H2, this will not show rotational spectra. Similarly, linear molecules. I have linear molecules. If I have CO2, the linear molecule C double bond O and double bond O on the other side also. It is a linear molecule. It will not have the permanent electric dipole moment. It will not show the rotational spectra. So linear molecules like BF3, I think those things will not show permanent. They don't have permanent electric dipole moment, and they will not show the rotational spectra. And what is the wavelength of the rotational spectra? What is the region of the electromagnetic spectra in which the rotational spectrum is seen? That rotational spectrum is seen in the far infrared or the microwave region. We'll discuss why it is in the far infrared region. Far infrared or microwave region of the electromagnetic spectrum, you will see the rotational spectra. So vibrational spectra is seen in the infrared region of the electromagnetic spectrum. The molecules which change, there is a change in the electric dipole moment of the molecule while vibrating. When the molecule vibrates, there should be a change in the electric dipole moment of the molecule. So H2N2O2 will not show the vibrational spectra because there is no change in the electric dipole moment while vibrating. So H2N2O2 as such, zero electric dipole moment, and vibrating also it will not show. So HCl has got certain electric dipole moment. While vibrating, it will change. There will be a change in the electric dipole moment with the change in the bond length as it vibrates. Okay, so vibrational spectra is in the infrared region of the electromagnetic spectrum. We will see why it is in those regions of the electromagnetic spectrum. So we should understand there should be a change in the electric dipole moment for vibrational spectra to happen. So there should be a change in the dipole moment during the vibrational motion of the molecule. I have mentioned it. So we are basically mainly discussing today problems on rotational spectra and the regions of the electromagnetic spectra in which the different spectra are, because the quiz questions are there with the different spectra regions of the electromagnetic spectrum. So I'll come to the rotational spectra, explanation of the rotational spectra. The EJ energy of the rotational state with the angular momentum J is equal to h cross square by 2I into J plus 1, where I is the moment of inertia. So that is equal to h square by 8 pi square I into J plus 1. J is the 0, 1, 2. So there will be rotational state. The selection rule for the rotational transition is delta J is equal to plus or minus 1, because the photon has the angular momentum 1 that you just look into. The wave number of the rotational state Ej by Hc is mu bar is Bjj plus 1. We know all these details. J is equal to 0, 1, 2. B is equal to h square by 8 pi square Ic. Okay, 8 pi square Ic B. So if you have the Bjj plus 1, when there is a transition from J is equal to 1 of the higher state to J is equal to 0 of the lower state, vibrational state, lower vibrational state, then there will be a rotational line you will get. Okay, so when it is in the same vibrational state, B is equal to 0 or B is equal to 1, it is transiting from J is equal to 0, 1 to 0, J is equal to 2 to 1. Like that, you will get the rotational line successively. You will get the rotational line, and Bjj plus 1, you will get the rotational lines at 2B, 4B, 2B for 1 is equal 1 to 0 transition, 4B for 2 to 1 transition. Like that, if you substitute the J value as the lower J value, J plus 1 to J, that J value, if you substitute that J value, you will get whatever the value of the spectral line, 2B, 4B, 6B, they're equally spaced in units of wave number. E divided by HC gives us the wave number, the reciprocal of the wavelength. So you will get the rotational spectra. Now further, the moment of inertia of the molecule. From B, I can get the moment of inertia of the molecule. From B, the rotational constant it is called. From B, I can get the rotational constant, that B, I can get the moment of inertia, h by 8 pi square Ic. B is equal to h by 8 pi square Ic. I can get the moment of inertia. From that moment of inertia, I can calculate the bond length. So I know if I know the mass, reduced mass of the system, I can find the bond length. So for that molecule, HCl or any other molecule, it is showing rotational constant. I can get B. From that spectra, I can get B. From that B, I can get the moment of inertia, and from the reduced mass M1 M2 by M1 plus M2, reduced mass I have from the directly the molecule, and from that I can get the bond length. From that bond length, so I have written that from observe that same thing what I'm explaining, I have written it down. So that is the theory of the rotational spectra. Okay, now I'll go to the regions of the electromagnetic spectra in which the spectrum in which these things are seen. Okay, the question reads: the typical wavelengths emitted by diatomic molecule in purely vibrational and purely rotational transitions are. So as a knowledge, you know that rotational spectra, microwave region or far infrared region, vibrational spectra, infrared region. So based on knowledge also you can write the option is C. So purely vibrational is infrared, purely rotational is microwave. Then I have written down electronic spectra is ultraviolet and visible region, vibrational spectra infrared region, rotational spectra far infrared or microwave region. What is the logic behind this conclusion? So electronic spectra, you know, the difference between if I take hydrogen atom 13.6 electron volts and 3.2 electron volts, 3.4 electron volts, the difference between that is a maximum when we compare electronic, vibrational and rotational. Next to that comes the vibrational spectra. The vibrational levels are a little less in energy. Hence the emitted, I have written, the energy difference is maximum for the electronic spectra. So wavelength is minimum. E is equal to Sc by lambda. So energy difference is maximum. So wavelength of the emitted line due to the energy differences is small. Energy is maximum and wavelength is small. That comes in the ultraviolet and visible region. Then the vibrational spectra levels, the energy difference is little less. In a given electronics levels, there will be several vibrational levels. So the vibrational energies are little less in energy, so more in wavelength. More in wavelength means it will go to the infrared region. And the rotational level still less in energy, so more in wavelength. So it will go to the far infrared and microwave region. So less in energy, rotational transition less in energy, more in wavelength, it will go to the far infrared and the microwave region. I have explained it fully in the slide over here. Now I'll go to the I have to say something about the electronic spectra. So just to give an idea and find out the actual wavelength of the slides, the wavelength of the lines in the electromagnetic spectra. You know, the Zeeman series is generated by the transitions from n is equal to n2 is equal to 2, 3, 4. These transitions 2, 3, 4 levels to 1, the first orbit or the ground state of hydrogen atom. And the Balmer series is generated by the transitions to the n is equal to 2. Sorry, there is a mistake in the slide. N2 is N1 is equal to, that should be N1 is equal to 2 and N2 is equal to 3, 4, 5. So if I want the first line of the Balmer series, this is the first line of the Zeeman series. First line of the Zeeman series, if I want, I will have to do a transition from N2 is equal to 2 and N1 is equal to 1. So that if I put it over here, N1 is equal to 1 and N2 is equal to 2. First line of the Zeeman series, I'll get R by 4 minus R, R minus R by 4. So it is 3R by 4. The wave number is get from this expression, wave number of spectral lines, wave number is equal to 1 by lambda is equal to 3R by 4. So wavelength is just 4 by 3R. The first line of the Balmer series, R by 9 and R by 4. So the wavelength of the spectral line wave number is R by 4 minus R by 9, R by 4 minus R by 9, pi R by 36, and the wavelength you will get the opposite of it, the reciprocal of wave number, so 36 by pi R. So in the next slide, I have calculated 4 by 3R values and 4 by 5 by 36R values. So for 36 by pi R and 4 by 3R values, and the R, you know, 1.097 into 10 raised to 7 meter raised to minus 1. The Rydberg constant is 1.0797 into 10 raised to 7 meter raised to minus 1. So we'll get the first line of Balmer series in the ultraviolet region, and the first line of the Zeeman series in the ultraviolet region, and the first line of the Balmer series in the visible region. So this is the I have derived it for your how, even if you want to know the basics of it, exact basics and exact line, we have explained it over here. And now you go to the match the following problem. So electronic spectra, which region, what is the centimeter raised to -1, what is the wave number, rotational spectra, and molecular dissociation. So if I arrange this in the trick is, if you want to solve in 10 to 15 seconds, the trick is you arrange in the increasing order of energy, and then inverse will be the arrangement in the wavelength, in terms of the wavelength. So what we can do, increasing order of energy. So rotational spectra is the lowest energy, electronic spectra more energy, molecular dissociation needs still more energy, molecular dissociation will require. So arrange in terms of energy and wave number are synonymous. So arrange in increasing order of energy, your same in terms of wave number, same sequence will be there. Rotational spectra, lowest wave number, vibrational spectra, more wave number than that. Then here we don't have electronic spectra, more wave number than that, and molecular distortion, more wave number than that. So the increasing order of wave numbers is 10 to the power 0 to 10 to the power 2, and 10 to the power 5 to 10 to the power 6, option 2, and then we have got 10 to the power 6 centimeter raised to -1. So electronic spectra will correspond to the second option. Molecular dissociation having the highest energy, it will correspond to first option 3-1, and rotational spectra have in this region third option 10 to the power 0 to 10 to the power 2. So this is the way. Instantly, if you want to solve such kind of problems in GATE 1 marks question or 2 marks question, you can go with the wave number, energy proportional to wave number, or energy inversely proportional to wave number. Just arrange those things in the order of increasing energy. So this is regarding our wave, the region of the electromagnetic spectrum in which the different spectrum are seen. So now I go to the rotational spectra. I'm solving another 1 or 2 problems on rotational spectra. So which molecules show rotational spectra, which do not? So the question reads: the molecular spectra of 2 linear molecules COO, carbon dioxide, and CSO are recorded in the microwave region. Which one of the following statements is correct? Which one of the following it is recorded in the microwave region? So we are talking about the rotational spectrum. Only the lines of the rotational spectrum will be seen in this region. So these lines are rotational spectrum lines. So the COO, as I was saying, is a linear molecule, and the dipole moment generated by CO in one direction is cancelled by the another CO bond, which generates the dipole moment in the other direction. Vectorially, it gets cancelled, and COO doesn't have any dipole moment. So we have written CSO shows absorption lines, and COO does not show absorption lines. So CSO has got permanent electric dipole moment and shows absorption lines. Okay, so this is the D option, which is correct. This is regarding the which molecules will show the rotational spectra and which do not show. Okay, so this is regarding my this thing. Then we go to the last question, which I am solving for the day. I have consumed some 40 minutes, less than some 40 minutes. So let us go to the question. It says that 3 consecutive absorption lines, the wave numbers of these lines are given, have been observed in the microwave spectrum of the linear rigid diatomic molecule.
Bhushan, just a minute. It looks like your laptop battery is low. It is giving some warning.
Okay. Just a second. Thank you. I'll connect. The laptop to connect. Okay. Okay. I'll connect. Just pause for 1 or 2 minutes. I'll connect the charger.
Yes, go ahead.
Okay.
Yes.
Okay. I'll start again. So absorption lines are observed for the linear rigid diatomic molecule in the linear rigid diatomic molecule. The wave numbers of these lines are given as given in the problem. So the moment of inertia IA and IB. Hello. The uh, the IA and IB, one is passing through there is a diatomic molecule, and you pass through the two atoms of the diatomic molecule. That is passing through the bond length. So IA one is passing to the center of mass, and another one IB is passing through the bond center of mass, but perpendicular to the bond length. IB is perpendicular to the bond length. So this problem is IA and IB. What are the IA and IB? By rotational spectra, we'll get the moment of inertia about an axis perpendicular to the bond length, because we can see, according to basic quantum mechanics, that the rotation about the symmetry axis, that is the bond length, if I rotate through that axis passing through the bond length of the molecule, the diatomic molecule, I will not get any rotational states. That is the basic quantum mechanics. And so according to that, my IA, which is defined as passing to the bond axis and passing to the center of mass, it is 0. So that IA is 0. Now we have to calculate IB. IB is what I have to calculate, and then as we have seen, the successive lines in the rotational spectrum, the 64.275, 77.130. So the successive line separation is 2b centimeter raised to minus 1. So 2b is nothing but 12.855 centimeter raised to minus 1. So the value of b I get from there, or 2b value I will substitute in the problem. 2b is 12.855 centimeter raised to minus 1. The p is equal to h by 8 pi square IC. So 2b is h by 4 pi square IC. Little tricky algebra is there, arithmetic is there. If you do intention, it will be a lot of problem over here, because again in the next thing you can, I think you can use h cross square by 2i, but again h cross square is also there in the answer, and h is also there in the bottom. H cross square is also there, and h is also there. So there you will be stuck up. There will be a lot of time consuming. You have to do it with a full mind. So 2b is equal to h divided by 4 pi square IC. So I is equal to I will go and I'll get h by 4 pi square into 2b. So after some mathematics, h by 2 pi I have taken it in. So from this h by 4 pi square, I take one h by 2 pi. I assign that value to be h by h cross, and then another 2 is remaining, and another pi of pi square is remaining, and then 2b is there. I have let this to be in the denominator. So 2b is also there, then c is there. So this is the main expression we have, and I will get from here. So that is again for getting h at the bottom. Get h at the bottom. I'll again have to multiply by h cross square here, and h cross at the numerator and at the denominator, h cross into 2 pi, I'll get h. H cross into 2 pi, I'll get h. So like this, if you do the 2b value, you substitute. So 2b value, if you substitute, that is 12.855, I'll get this in terms of, if this we can get in terms of the CGS unit, which we get, the answer is the IA is 0 and IB is the h cross square by 12.855 HC. So don't get confused with half the value of B, 2B, that is 6.427. So that is one of the thing, and 0, both are equal to that value, or 0 and I and IB 0 and other value. Okay, so it will get, because it is in the centimeter raised to minus 1, we will get the gram per centimeter square, moment of inertia in the gram per centimeter square. So my references are generally for atomic spectra white, HE white, atomic spectra HE white. It is now available in the printed version, is available in the market now. Up till now it was not available. HE white atomic spectra for atomic spectraless couplings and Zeeman effect, or entire for all singlet, triplet transitions, 2 valence electrons and all that. Zeeman, this HE White is a very good book. And for molecular spectra, you can use some simple books by Indian authors, Maxwell, Banwell and all that. Otherwise, Herzberg is there for molecular spectra, or some other Indian authors if that is required. And then the molecular spectra and laser and fiber optics. I think it is better written in. I have not covered it. You have to cover it separately. So that is the Ghatak book is there. Thank you very much for your kind attention. We'll be going for the interaction session, and my email ID. My email ID, the internet is an internet. Email ID is I've written Bhushan, Bhushan AK79 @gmail.com. Okay, the email ID.